So as I mentioned, the chi-square test will be broken down into two separate tests, one of which is called a goodness of fit test. That is our one-way chi-square. So the goodness of fit test uses sample data consisting of frequencies to test hypotheses. The test determines how well the sample data fits population proportions. For example, a researcher may be interested in of the two leading brands of smartphones, which is preferred by most people in the United States. Another question you could ask in this space is, in the past 10 years, has there been a significant change in the proportion of 12-year-olds who have their own cell phones? Now, with the first question of the two leading brands of smartphones, which is preferred by most people in the United States, you can imagine that we would be asking people, do you own an iPhone or do you own an Android phone? And when people respond, with their answers, we would categorize them based on their responses. So person one says Android, person two says Android, person three says iPhone, so on and so forth. That data is going to be nominal data, right? We are collecting categories. We are looking at categories that makes them nominal. We cannot rank them, even if we have personal biases around which of these phones we think is better. In actuality, there's no, objective criteria by which we can use to say, well, an iPhone is ranked higher than an Android, so on and so forth, which means it is not an ordinal variable, it is a nominal variable. For the second question, in the past 10 years, has there been a significant change in the proportion of 12-year-olds who have their own cell phones? Imagine what that would require in terms of collecting that data, right? We would be asking people, does your 12-year-old have a cell phone? Yes or no? And those responses are categorical. They are not, this is a nominal variable. So these questions are asking about population proportions, or how many people in the population have X characteristic. We are not measuring numerical scores. Rather, individuals are grouped into categories: Android versus iPhone. I accidentally wrote 10-year-olds or with phones versus 10-year-olds without, but the prompt is based on 12-year-olds. And we want to know which proportion of the population is within each category. In order to compute a one-way chi-square or a goodness of fit test by hand, this formula to the right, x squared, which is chi-square, equals the sum of the observed frequencies minus expected frequencies divided by 2, squared, and then divided by the expected frequency. I'm showing you this formula. If we were doing this by hand, I would show you the process by which we can calculate this by using a table. However, I'm not asking you to hand calculate this. I want you to know what it is that's happening in the background with SPSS, but I won't be asking you to hand calculate this test. There's also a unique degrees of freedom formula for the goodness of fit or one-way chi-square, and you would calculate that by degrees of freedom equals k minus 1. Remember, k equals your number of groups. For this slide, I wanted to show you that our null and research hypotheses, how you would write them for a goodness of fit test, as well as the concluding statement. For your null hypothesis, you would say there's no significant difference between the observed frequency distribution and the expected frequency distribution. For your research hypothesis, you would say there is a significant difference between the observed frequency distribution and the expected frequency distribution. Remember, as you are, incorporating this into your SPSS assignments, you want to make sure that you are including the appropriate context based on the test that you're conducting. And then your concluding statement would be there is or is not a significant difference between the observed frequency distribution and the expected frequency distribution. Therefore, we retain or reject the null hypothesis. With regard to reporting your results, this test, this image that you see on the left here is the output for a chi-square one-way or goodness of fit test. This particular test is using the sex variable. I will upload separate videos taking you through how to run these tests within SPSS. But this sex variable is the variable within our data set, the 1K survey. We had 453 males individuals who identified themselves as male, 609 individuals who identified themselves as female. Remember that there is our observed frequency. This is the data we collected. However, there is expected frequencies. Those are what we expected to see. And so because of the formula that we can calculate the expected frequency for the goodness of fit test, remember that we're adding our frequencies together, dividing by 2. So we expected to see 531 males. We expected to see 531 females. But notice that our observed frequencies do not reflect those expected frequencies. And so this residual column actually indicates the difference from your observed frequency to your expected frequency. So what this is suggesting is that there are minus 78, which is to say there are 78 fewer males in this sample than we expected. And this secondary residual number indicates that there are 78 more females than we expected. This test statistics window is indicating to us the results, our test results. So this is to say that our chi-square statistic is 22.915 or 22.92. We have degrees of freedom of 1. And then we have this slightly different looking significance number. With previous tests, we've seen sig be the only part of identifying our probability for that particular test. This asymp is actually short for asymptotic. That's an attempt to ensure that our variable is meeting a normal distribution. Not expecting you to remember that. However, this value here, whatever your probability value is here, that is what you are comparing against 0.05 to determine significance. As always, if it is greater than 0.05, it is not significant. If it is less than 0.05, it is significant. According to the results of this particular analysis, we do find significance. So there's a significant difference in the observed and expected frequencies. In order to report that in APA formatting, we would write a chi-square goodness of fit test was conducted to determine whether the frequency of sex was equally distributed across categories. The results were significant. We have this x squared symbol. We have 1 n equals 1062. Close parentheses equals 22.92, comma, p is less than 0.001. So what are each of these values coming from? I placed this statement down here to indicate to you all that the information you're drawing does come from the tables. Our degrees of freedom is this first number here, that is the 1. You pull this from this area under test statistics. N equals, and then you would input your sample size that's listed under this sex table. This is the table related to your variable. We have equals whatever your chi-square value is for this particular test, 22.915 or 22.92, comma, p equals, and then your p-value. In this case, while I included an equal sign here, if you had a number that did not, if this significance number did not show a less than symbol, then you would write p equals whatever the value is. In this particular case of this statistic, we saw that p was less than 0.001, so we replaced the equal sign with the less than symbol. As the statement that kind of wraps up what it is that you're studying, the observed frequencies differed significantly from the expected frequencies, with females, that should have an S, having more responses than expected. And so that's it for your goodness of fit test. That is your one-way chi-square.